Yeah, so Zaccharie is a PhD student in third year, I think now, in the parietal team, and he's going to present some work on how to do fast MRI reconstruction that he did for a challenge for the fast MRI challenge organized by Facebook, where he won the second spot, I think. All right, so Zachary, the stage is yours now.
Okay, cool. Can you all see my screen?
Yes.
Okay, cool. Thank you very much. Thank you, Thomas, for the introduction. So today we'll speak about the XPDNet for brain multicolor MRI reconstruction. And I will first start by trying to summarize in 3 pictures what is MRI. So you may be familiar with it. It's basically the scanner you use when you have a problem with your head or with your knees. And what it stands for is magnetic resonance imaging. So indeed, in MRI, we're trying to probe to image soft tissues. And so we do not directly take a picture, a photography of it. We use a physical phenomenon called resonance. And this physical phenomenon is happening thanks to a big magnet that we have around the organs to image. And in this particular setting, we're talking about the resonance of the hydrogen atoms in the water molecules of the body. And when we are doing MRI, what we obtain is not, like I said, the picture of the image. We obtain measurements, and these measurements, which are described here by YJ, have to be reconstructed in order to obtain the anatomical image of interest. So in the talk of Emily, I'm quite lucky because I think she used the same notations as me. So basically, X is the object of interest and Y is the measurements that you have. And here, the matrix that was called H in the previous talk is now replaced by two matrices F and S, which are basically combined together representing the matrix H of the previous talk. And so basically this F and S represent how we do the acquisition, so how we degrade our anatomical image. So this S basically represents the fact that we do not have only a single measurement channel for a given anatomical object. We actually have several receiver coils. As you can see here in red, all these little red squares are receiver channels, which are going to receive some signal from the object. And so this means that for each of these, we are going to have a measurement set. And basically, this else tells you how each receiver coil is sensitive to which region of the object, because this receiver coil, for example, is going to be much more sensitive to the signal coming from the top of the head compared to this other receiver coil, for example. Then the measurement is actually acquired in the Fourier space of the image. So this means that we are not going to project the image like in Emily's situation. We are here rather going to take the Fourier transform of the image, and we are going to take the undersampled Fourier transform of the image. The reason why we're going to take the undersampled Fourier transform is because we want to spend less time acquiring data, and each line of Fourier transform actually takes some time to acquire. So if we want to accelerate the acquisition, we have to take less Fourier lines. And this means that we do not have the possibility to simply inverse the Fourier coefficients anymore. We actually have an idealized inverse problem. So for those of you who want to know why it's idealized, because of course here I didn't put the noise, and there are also some conditions in which the approximation of the Fourier transform are not verified, such as problems with magnetic field inhomogeneities. And so, as we did in the previous talk, when we have an idealized inverse problem, we are going to try to solve it by formulating an optimization problem. So, as we saw before, the optimization problem is typically composed of two parts. So you have first a data consistency, data fidelity term, which is here embodied by this L2 norm, and you also have a prior term, so a regularization term, which is here kept very generic. It's R of X. And when we solve this this optimization problem, typically we are going to use, as Emily showed, a proximal gradient descent. But when someone like me who does deep learning sees a situation like this, I am wondering what I can do to learn all the parts that are learnable. And indeed, in the case of MRI, it's interesting to learn some parts because we would like to get better image quality, and we would also like to have a reconstruction process that is much faster than what is possible with current iterative reconstruction techniques. And so the first part that we can look at is actually the optimization algorithm parameters. So, for example, you can think of the step size of the optimization algorithm, or you can think of the acceleration momentum when you use acceleration in gradient descent algorithms. The second part that you can think about is actually the noise model. So this data fidelity term, so the L2 norm, actually stems directly from the noise model that we have, which in this case would be an additive white Gaussian noise. But what we can do if you think that this additive white Gaussian noise is not necessarily exact is we can try to learn the equivalent of its gradient. And the next thing that's in this equation we see as a big problem in the context of MRI reconstruction is actually the sensitivity maps that we were talking about earlier. So the matrix that represents which part of the organ you are more sensitive to. And generally they're computed using a method called L1 spirit, but this method is inexact, and ideally we would want to have a way to know from the data what these sensitivity maps are. And so what we're going to see is that we can learn how to refine estimates of sensitivity maps. And finally, and I think more importantly, is the prior term. So usually it's set by hand, and you saw in the previous talk how it could be set. So it can be a Tikhonov regularization. It can be an L1 norm over some coefficients in some appropriate basis. So for example, in the wavelet decomposition of the image. And so all of these are really good, but they're not completely well suited to the data at hand. And we're going to see how we can learn an equivalent of this. Sorry, not an equivalent, but how we can learn this prior term, not by learning it directly, but by learning the equivalent of the proximity operator of R. So if I summarize the outline of what I'm going to try to show in terms of modeling, we're going to first look at how the cross-domain learning framework allows us to learn all of the things I talked about, and in particular the optimization algorithm parameters. We're then going to see how, in the particular case of MRI reconstruction, we can try to refine the measurement operator. And in particular, how we can try to refine our knowledge of the measurement operator. We're then going to see how we can learn the proximity operator of the prior term. And finally, how we could go about trying to learn the data consistency, which in turn means learning the noise model. But first, with the cross-domain learning. So the key intuitive idea in cross-domain learning is that when you have a reconstruction, you're going to try to correct your reconstruction, and you're going to try to correct between the image domain and the K-space. So yeah, I didn't mention it, but the K-space is actually the little name that we give to Fourier measurements in MRI. So you can think of, when I say K-space, just think Fourier space, and you should be fine. And so yeah, we're going to try to alternate the corrections between the measurement space and the image space. And while doing so, we're going to try to compare always the original measurements with the current measurements that we have with our solution. And the tool for that is the unrolling of optimization algorithms. So basically, when you want to learn all the things I've talked about, you're going to take an optimization algorithm, unroll it for a certain number of iterations, fix it, and then you're going to learn some parts of it. So when you write an optimization algorithm, you're going to have two steps, as I said. So first, you're going to have this step corresponding to the data consistency gradient step. And so in this case, you can see that it operates as kind of a correction in the measurement space, in the K space, because here the correction is happening here. You have the residual. And then you have a correction more in the image domain, where you have the proximity operator of the prior term applied to your current solution. And what you can do is now simply say, okay, I'm going to replace this element by, for example, a neural network. And this is exactly what you can see here in this illustration. So for a cross-domain learning, you're going to have a fixed set of unrolled iteration NC, and you're going to put in your measurements. Your measurements are going to be refined by data consistency and potentially a correction in the K-space. And then you're going to go back in the image space using the adjoint of your Fourier transform. And in the image space, you're going to perform as well any image correction that you want with typically a fully convolutional neural network. And like this, you're going to alternate the correction between the two spaces and obtain a final image. And when you train this network, you train it end to end. That is, you're going to apply a loss to this reconstructed image, and you're going to learn all the parameters in the networks via gradient descent, and the gradients are computed with backpropagation. And in the particular case of the XPDNet, what I did was to take the idea of Adler and colleagues who unrolled the PDHG. And in this particular case, what's interesting is that in their network architecture, they used a buffer of solutions. And basically, what they claim is that this buffer of solution allows them to learn a nonlinear acceleration scheme. So which is quite interesting because it allows the network to converge faster to the solution. Also, one small specification is in that in this case, I didn't use a K-space correction network. I just used the residual, so I just basically did not learn the any part of the data consistency, but I will come back to that later. So now we have seen the framework of cross-domain learning, and I'm going to show in this particular case how we went about the measurement operator refinement. So in this case, when you want to derive sensitivity maps, a nice first approximation is to basically take your input k-space, select only the low frequencies, and perform the inverse Fourier transform. And with this, you're going to have a series of very blurry images, and each image is going to be slightly brighter in the region where the coil is receiving the most signal. So here you can see that the coil is receiving the more signal in the lower left part. And what you can do is that you can learn a unit on top of this first estimate of the sensitivity maps. So this unit is applied only once to all the sensitivity maps, and basically is going to refine this coarse estimate of the sensitivity maps. And then you can use these sensitivity maps as if they were the true ones within your networks. And because we do not have access to the true sensitivity maps for each data, basically we're also going to learn this end-to-end. So we're just going to plug in this sensitivity maps estimator, and we're going to let the gradient flow through to learn the parameters of this unit. So now we have seen the measurements operator refinement, and now onto the proximity operator learning. So the proximity operator, which was the image that you saw in the illustration earlier, is basically going to take in an image and try to remove the noise or de-alias it. You can think of many words for it, but basically it's going to try to make it look more like a typical MRI image. And so this proximity operator is strongly related to denoisers, because basically denoisers can be seen as an application of the proximity operator of an unknown function. So what we did is that we benchmarked several denoisers in a simpler context, which is basically a context where we do not have multiple coils, we just have a single coil. And we try to select the one which had the best performance. And in this particular case, it was the multi-level wavelet convolutional neural network, which had the best performance. And so its architecture is quite typical. So basically, it's a unit, and you just replace the pooling operation with a wavelet operator. And so this architecture gave us the best results. And I specify here that we do not use batch normalization because we usually have a batch size of 1 in our training. And now finally onto the learning of the data consistency. So a strong disappointment, I think, but I didn't use it for the challenge I took part in. I didn't really have a good reason for it. I didn't benchmark it, but I thought that memory was going to be an issue. So, and actually I can say it now with certainty, it's actually an issue because if you use data consistency learning, you're going to increase the size of your activations at each iteration, at each unrolled iteration of the network. And so you're going to have a trade-off between using more unrolled iterations and using data consistency learning. And at this point, using my networks, it's better to use more iterations rather than data consistency learning. But if you wanted to use data consistency learning in a setup where memory was not an issue, then basically what it would amount to, is to add a convolutional neural network at this stage here. So basically, when you're doing the proximal gradient descent, here when you're doing the gradient of the L2 term, you would correct it. You would learn how to correct it best with a convolutional neural network. So that was it for the XPDNet. Now I'm going to move on to the experiments and the challenge. So the data that we used to train the network was the fastMRI dataset, which is a dataset which was released by Facebook and NYU in 2018. And for the brain data, it's composed of roughly 4,500 training volumes, which represents about 1 terabyte of data. And because we have access to the actual raw data, we retrospectively generate the undersampled case space. So I'm going to move on quickly to some training details. So I think that what's important is that I use the Radam optimizer. So this optimizer is very interesting because the authors claim that it's strongly independent of the learning rate. So basically, the performances that you're going to get are going to be roughly the same no matter the learning rate that you choose. The total number of gradient steps that I did was about 500,000, which means that I took 1 week of training for my network, which had roughly 150 million parameters. And the loss that I used, so which is the last point, is a compound loss between the L1 difference and the MSSIM, so the multi-scale SSIM, as was done by the previous winners of the challenge. And now on to the results. So I'm going to directly dive into the challenge results. So the challenge was done in 2 tracks. So you had 2 different acceleration factors, which basically mean that which basically relates to the number of lines that you're going to acquire with respect to the total number of lines in the case space. So basically, the higher the acceleration factor, the faster the exam is going to be, but also the easier it's to the more difficult it is to reconstruct the image. So with an acceleration factor of 4, which is a mild acceleration factor, you had PSNR levels of around 41 to 42. So you can see a pretty big gap between the second and the first competitors. And so with my network, I finished third in the quantitative evaluation. And it's about the same story for the acceleration factor of 8, so which means a faster exam. But you can see that the PSNR levels drop quite significantly. However, what was interesting in this fastMRI challenge is that the evaluation was not done simply with the quantitative matrix. They also reached out to several radiologists who rated the images on different qualitative aspects. And so with this qualitative assessment, my network was evaluated to be better than the one that was previously second. And so I ended up to be the official runner-up of the challenge. And so if you want to see some images, basically those are the typical images that you get. So on the left, you can see the reference image. In the middle, the reconstructed image with the XPDNet. And on the right, the difference between the two. And so this line here is just some artifact present in the original reference image. And so you can see that it's pretty difficult to visualize any difference between the reference and the reconstructed image, which means that, and as was said by the radiologist, that the networks are pretty much mature for the acceleration factor of 4. However, at the acceleration factor of 8, the picture is quite different because you can start to see some differences between the original and the reconstructed image. And you can also see, for example, a loss of contrast, some blurring as well, which makes it difficult for the radiologist to read the images. So I have different images with different types of contrast. I can show them to you if you want, but I will move on now to the reasons why I'm only second. Because this is a question that I get a lot. What did the winners do better than you? So it's a bit unclear because the winners, I think they do not want to open source their solution, or they do not want to publish anything related to their solution. And they however did a short oral at the NeurIPS medical imaging workshop. And so they used something that they called feature level multi-domain learning. So it's a bit unclear what they did here. I think it's not clear as well that they used 3D post-processing because the main network is in 2D. And I also think that they use a better training than me, so it was distributed training for a longer time. So I think that's also part of why they reach better results. And so now I'm going to conclude and talk a bit about the future steps for me. So I really wanted to highlight that the XPDNet is more than just learning the prior, learning the proximity operator of the prior, which is often what is thought of the unrolled networks. It can also learn the unrolled optimization structure. It can learn to refine the measurements operator, and you can learn the noise model. And using all this machinery, of course, without learning the noise model, we managed to achieve the second spot in the fastMRI 2020 challenge, which means that this is an excellent type of framework, and it's very modular to tackle inverse problems. So the next steps I have on my plate are, of course, to implement the data consistency learning, which is something I actually already did, and to use post-processing, better training, and multi-domain learning. I'm going to try to incorporate the elements of the solution of the winner in my solution. But it's unclear whether this is going to bring substantial improvements because I really don't know exactly what they did. What could also be interesting in the direction of research is to go with a fully 3D model using, for example, techniques like model parallelism. So basically, trying to benefit from multiple GPUs to parallelize the convolutions in the network. And the final step I really want to dig into is the implicit deep learning, which seems to be very well suited to the unrolled networks for inverse problems, and that could alleviate a lot the memory problems that we currently have that limit the size of our networks. Just a few acknowledgements. So we did all this using the Janzé supercluster which is full of V100 GPUs, and basically it's a supercomputer that you can have access to with 10K hours of GPU just by submitting a simple request. So don't hesitate to ask me questions about it or refer to the user doc. I think it's a really great tool to do better science. And of course, all the code is available in the TensorFlow framework on my GitHub. So thank you for your attention, and I will now take any questions. Thank you very much.
Thank you very much, Zach, for this very interesting talk. So, is there any question in the audience? All right, so maybe let me ask a question. In the challenge, there are like different type of. I think there are different type of images. So were you able to learn a single network to be able to solve to reconstruct image from, for instance, the knees or the brain, or did you have to have specific networks for each tasks?
So what I did in this particular case was just a network for the brain, and I'm going to be even more specific. There is one network for each acceleration factor.
Okay.
So I didn't test this specific network on another organ, but it's part of the job of an intern that is about to come to the team. So we will try to see with her what we can do in terms of transfer learning, how we can adapt to other organs. What I can say though is that the network is able to reconstruct images with different contrasts. So in MRI you have different contrasts, and so the network is able to tackle all these different contrasts, and also it's able to tackle, I would say, out of distribution brains, so brains that are not necessarily at the same resolution, or that have not been acquired in exactly the same conditions.
Oh, so there are some kind of like generalization of the network. You don't have to learn for every single task, but like there are still some kind of consistency in the task.
Yes, exactly.
Yeah, and yeah, maybe on the 3D. Oh, go ahead, Olivier.
Okay, sorry, I didn't want to interrupt. So my
No, go
question
ahead.
is, did you do some kind of ablation study to study which part of the component of the equation that you learn are the most important to learn, and which parts you could keep fixed without degrading the performance too much?
So no, I didn't perform an extensive ablation study. Unfortunately, it's a bit costly, I would say, but it's not a good excuse, of course, but it's still one of the excuses I have. I did perform involuntarily an ablation study because I simply didn't use the sensitivity maps refinement at the beginning, and you could see that for the same network, if you do not learn the sensitivity map, so that is, if you do not try to refine the measurements operator, you're going to lose a few points in PSNR. So you may be going to lose 2 points in PSNR.
Okay, thank you. And you mentioned that you already tried the data consistency learning that you did not do at the beginning, and you have
yes.
results on this?
Yeah, I had results. Actually, I have a lot of preliminary results for all these parts, but I didn't want to talk too much about it. So basically, for the data consistency learning, as I was saying, the problem is that you increase the amount of activations substantially, especially because you're in the case space, so you have multiple coils, which means like multiple times the amount of activations, and so this means that you have to do less unrolled iterations. But doing more unrolled iterations allows you to have more capacity, and actually it's a trade-off between having more unrolled iterations and having the data consistency learning. In this particular case, for my network, what happened is that it was slightly better to do more iterations rather than to do data consistency learning. But I could not speak for all the cases. And all the other parts which I mentioned, which were the post-processing, the longer training, and the multi-domain learning, for now it didn't give anything, so I'm a bit clueless as to what they did exactly in their network. I think I'm going to just ask them via mail and hope for them to be nice to me, but I'm not sure.
So it means that if you can reduce the memory usage by doing a model level parallelism, you could potentially benefit from data consistency training with more iterations.
Definitely, yeah, exactly. So this is one of the big points I think at this stage that I want to underline in the practical application is that my model is clearly limited by memory. So I have rather small models for the image correction, and I also have I do not have the leisure to use the data consistency learning, and I do not have a lot of I would say I do not have a huge amount of enrolled iterations. I think that if there are some techniques that can alleviate the memory problems, either practically like model parallelism, or even theoretically like gradient checkpointing, inverse models, or reversible models, or implicit deep learning, is definitely a track to look into.
And maybe some kind of tensor factorizations of the convolutional kernel or stuff like that, or maybe
that I do
actually
not know.
the activation maps that is problematic, so maybe that won't change this.
Okay. Yeah, the problem is not the number of parameters, but the size of the activation.
Yes.
Yeah, exactly. For now, the number of parameters is actually relatively small.
There are some. We should talk again, but there are some way to alleviate this for like if you have like accelerated when you have momentum. This is the work by Pierre Ablin. I think you know about it, but when you have momentum, you have some kind of way to make your model inversible. For when you have data consistency, and then you can like you're bound by CPU and not by memory anymore, because it's like you have much lesser memory requirements. Okay.
We should talk about it, yes.
And maybe gradient checkpointing would be nice, because this means that you can, if you can already unroll like 2 or 3 iterations, then you can checkpoint every 3 iteration. It's kind of okay.
Yes.
But yeah, it would be interesting to talk about it.
Sure.